Okay, good morning, everyone. Welcome to the GIS Sea Level Rise seminar. Today we have Dr. Yu Dong. Uh, she is a NOAA Climate and Global Change postdoctoral fellow in the Ocean and Climate Physics Division of the Lamont Doherty Earth Observatory, and her research utilizes global and idealized climate model simulations and observational data to study large-scale climate interactions in the coupled climate system and how these dynamic processes are coupled with Earth's radiative responses and climate sensitivity to anthropogenic and natural forcing. Dr. Dong earned her bachelor's in international development engineering from Tokyo University of Technology and her PhD in atmospheric sciences from the University of Washington. And today she will be speaking on the topic global impact of Antarctic ice sheet meltwater on climate sensitivity and transient warming. So welcome. Oops, I think now we can't hear you again. Can everybody hear me? Yeah, I think so.
I can hear you, but not UA.
Shaina, I think you wanted to mention a AGU session. Maybe you could do that now if you want.
Sure. While UA is getting the audio sorted out, I'm super excited for her talk. Her and I have collaborated on some of the work she's presenting today, and she's just such a brilliant researcher. So first of all, I'm very excited and hoping that her audio difficulties get sorted out momentarily. Just in case folks are interested, since this is a sea level seminar, I thought I'd mention that at AGU this year, Ruthie Halberstadt and I are hosting a session on let me grab the exact title, Interdisciplinary Sea Level Rise Research to Address Social Justice and More Than Human Impacts. We're looking for like a very broad lens on interdisciplinary sea level rise research. Our invited speakers are Dr. John Barnett, talking about impacts and responses to sea level rise on the front lines, evidence from local people across the Marshall Islands. And our second invited speaker is Dr. Roseanne Marder-Kohler, speaking about loss and damage implications of sea level rise on small island developing states. So while the two invited speakers are focusing on island state impacts, we are looking for a very broad and wide-ranging audience, and I will put the thing in the chat. So hopefully UA's sound is working now.
Oops. Looks like maybe it wasn't. Okay, we'll wait a little bit. I think she might be trying to reconnect.
Hello, can people hear me? I
Yes.
just quickly, oh great, I just quickly restarted my laptop.
Okay. Okay. Good.
I think, did you say something? I think I totally lost your introduction
Okay.
or something. Should
Okay.
I
Yeah.
start now?
Sure. Yeah. Yeah.
Yes, sorry everyone, sorry for the trouble. I think something wrong with my laptop or on my end. Well, I missed your introduction, Patrick, but thanks for assuming, yeah, you give me an introduction. So thanks so much for inviting me. Yeah, I'm very excited to speak to you all about our recent work looking at the global impact of the ice sheet meltwater on climate sensitivity and transient warming. I don't know if, well, my background and my past study has been mostly focused on climate sensitivity and global climate dynamics. So I personally wasn't very much involved in a lot of work focusing on ice sheets melting or sea level rise per se. But it has been a fun collaboration for me. And thanks to my collaborator, my colleague, Andrew Pauling at the University of Washington, and Shaina, who's on the call here. I'm so glad to see her here, for kindly providing me with their Antarctic ice sheet meltwater simulations, so I can and share their wisdom with me about ice sheet melting, so I can apply that to study remote impact of or teleconnection from the Southern Ocean to the tropics, how these large-scale interactions shape the global sea level temperature patterns, and therefore eventually feedback onto climate sensitivity and transient warming. Yeah, so let me start. So not sure the general background and interest of this community, so I'm probably gonna spend some time talk about climate sensitivity, mostly where I come from, why I think why I decided to apply this ice sheet meltwater to study climate sensitivity, why I think this connection is important, and this is mostly through a recent topic called the pattern effect, how large-scale sea surface temperature patterns influence climate sensitivity. And second, to further constrain or understand the pattern formations, I'm going to apply this ice sheet meltwater simulations, and I'm going to talk about what we learned from this ice sheet meltwater simulations about local and remote impact of meltwater on global SST patterns. And part three, finally, I'm going to combine all of these pieces together to talk about impact of meltwater on global transient warming in the context of energy budgets. So part one, ECS, equilibrium climate sensitivity, is essentially defined as long-term or equilibrium global mean surface temperature change caused by a doubling of the CO2 above its pre-industrial concentration. So pretty simple index, just we double CO2 and see how much warming we're gonna see in the long-term equilibrium timescales. Although it's a very simple index, it's a widely used concept in our climate science community, and it's been a useful framework for us to compare results from models, observations, and paleo record across multiple lines of evidence. But for those of you who are not familiar with ECS, you may think of it as a very idealized and equilibrium long-term warming. I want to spend a couple minutes to talk about why we cared about, why we study ECS. One of the reasons is because although it sounds like very equilibrium, like thousands of years later, it's actually a good predictor of near future warming as well. So in this recent Sherwood paper, this WCRP ECS report, we found that the vertical is the model projected global warming at the end of the 21st century, and the horizontal is the model's ECS values. So cross forcing scenarios, each dot represents one of the semi-5 couple climate models. And you can see ECS explains a large variance in the projected global warming at the end of the 21st century, meaning that ECS is also a good predictor of 21st century warming as well. So it matters for transient timescales as well. And second, this quantity actually links to many important physical mechanisms, especially those we call it as radiative feedbacks. So I know people here probably most of the times looking at sea level rise or ocean surface temperatures. But for a second, let's consider this Earth as a pole, and let's look at top atmosphere. So when you have radiative forcing, for example, due to CO2 doubling, then you have positive radiative forcing down to the Earth's warm surface temperature. And with global warming, the Earth emits more radiative flux at the top of the atmosphere to balance this radiative forcing. This total amount of radiative response is thought to be proportional to the amount of the surface temperature change. And this coefficient lambda is what we define as radiative feedback parameter. So you can see its unit is watt per meter square per Kelvin. So it's radiation per unit of a surface temperature change. So it physically just represents the efficiency of the Earth's radiative damping. So usually we see larger feedback or stronger feedback means, or more negative feedback means the Earth is more stabilizing, so it can efficiently respond to radiative forcing. So it doesn't have to work that much to balance this radiative forcing. On the other hand, we see if we say smaller feedback or smaller magnitudes or less negative feedback means the Earth is less stabilized. So it has to warm a lot, the bigger delta T to compensate this total amount of radiation changes. And this feedback consists of a lot of physical processes such as Planck feedback, so black body radiation, and changes in clouds, water vapor, sea ice, lapse rate accompanied with this global warming. So at the top of the atmosphere, at any transient timescales, you have forcing, you have a response, but there might be some residual, it's called radiation imbalance, we can detect from satellite remote sensing products, or this at global mean spatial scales, this is essentially the amount of heat taken up by the deep ocean temporarily. So you can think of it as ocean heat uptake. But at equilibrium timescales, when there's no residual anymore, the ocean no longer takes up heat at true equilibrium, then the temperature change at that timescale is essentially governed by forcing and feedbacks. So when we say ECS, equilibrium climate sensitivity, which is essentially the equilibrium surface temperature change to CO2 doubling, is essentially determined by how much forcing from atmospheric radiative forcing due to CO2 doubling, and how strong the feedback is at that equilibrium scales. And so far, we made good progress constraining forcing from, for example, line-by-line radiation model or other model simulations. But feedback, this lambda term, still remains the biggest uncertainty source, especially the cloud feedbacks remains hard to constrain. So for decades, the whole community tried to constrain ECS from 1.5 degree to 4.5 degree, but still this uncertainty range remains large. So there still remains a big science question to understand ECS and various process constrain the ECS, climate sensitivity. So what is exactly range of ECS estimate? Turns out if we use historical energy budget constraints, for example, we use what we observed over the recent decades or over the past historical period from satellite remote sensing or Argo flow ocean measurement to get the global energy, observe the global energy imbalance, forcing a surface temperature, and we'll combine all of this term together to come up with climate sensitivity estimate based on this observed historical energy budget. We end up with a pretty low range of climate sensitivity centered around 2 degrees. This is from historical observations. But then if we run a climate model with abrupt CO2 doubling or quadrupling and then normalize, we end up with a climate sensitivity range quite higher than recent observations. You can see this is a clear discrepancy between these two estimates. So when this paper came out, when the observed energy budget, observed estimate came out, a lot of people started to worry why this model-based ECS values are so high. Does that mean that our models, especially the atmospheric model physics, cloud physics, they're too sensitive to CO2 forcing, so these ECS values are too high relative to observations? But over the past decades, we start to realize that this may not be a clean comparison. For this black line, that's observed energy budgets. So this energy budget is from observed historical period, while for model simulations, to doubling or quadrupling, the energy budgets is totally derived from different states. It's future states. So they're not looking at the same time period. So it's not clean comparison. We want to compare models with observations at the same time period, keeping all the other variables the same. So we bring in another set of simulations called AMAP simulations. So these are same ECS estimates from atmosphere only models. So we take atmosphere models and prescribe them with observed CS of temperature trend and CS concentration over the same historical period. And now we find same atmosphere model, but if they're saying they're realistic CS of temperatures, they do a pretty decent job reproducing this low range of climate sensitivity, quite in line with observations, even though their counterpart fully coupled models under CO2 quadrupling on the future CO2 increase scenarios tend to produce higher climate sensitivity. So the key point here is for any pair of pair models like orange model versus orange simulation versus their counterpart fully coupled models, the discrepancy is not because their S-inferior model physics is wrong or biased. It's simply because the same S-inferior model is looking at different SST, system temperature patterns. For AMIP simulations, for our historical observations, we have this observed historical SST pattern, which features a cooling trend in the Eastern Pacific and the Southern Ocean, quite unique SST pattern. Well, for model projections under CO2 forcing, models generate their own SST patterns. They tend to favor this equilibrium SST pattern with enhanced Eastern Pacific warming in the Southern Ocean, which looks totally different to the recent observed SST pattern. So that's the essence of the pattern effect. In other words, it's the difference in SST patterns that change cloud feedbacks or water vapor feedback, and therefore change the estimate of energy budget and climate sensitivity. So far, we think that climate sensitive or feedbacks are constant with time. They just depend on how much global mean warming you will get. But now we realize over the past decades, a lot of studies start to suggest that feedbacks or cloud feedbacks, water vapor feedbacks, climate sensitivity actually very sensitive to the spatial distribution of the SST anomalies. And as SST anomaly or this distribution pattern change with time, then your estimate of a climate sensitivity will also change with time. So any estimate of a climate sensitivity from this transient state might be essentially biased compared to the true equilibrium or long-term climate changes. That's why sometimes we refer to this climate sensitivity from a transient state as effective climate sensitivity. I don't want to spend too much time digging into this mechanism of the pattern effect. It's just to show a nice schematic from IPCC-R6 and a lot of recent studies try to use S-inferior model simulation to study the mechanism why we see different SST patterns give you different climate sensitivity and the feedbacks. Especially over historical period, we see this lower climate sensitivity corresponding with stronger cloud feedback is because this tropical Pacific SST pattern. So you have this La Nina-like cooling pattern with strengthened west-east gradient, which means more warming in the West Pacific warm pool regions and the cooling in the Eastern Pacific, the cold town regions. And this warming from the warm pool regions can be efficiently transported to the upper troposphere and then spread it out through the whole troposphere because essentially the tropospheric temperature is set by this warm pool regions. So the key point is over the Eastern Pacific, where low clouds usually grow, then you have warming aloft, but then the surface is cooler, which means this climatological inversion drift gets increased or gets strengthened. And this condition favors low clouds. So this condition, the ST patterns lead to more low clouds to grow in this Eastern Pacific. And low clouds are type of clouds that are very efficient at reflecting shortwave radiation. That's why this whole pattern, this west gradient, essentially drives more low clouds that can reflect more shortwave radiation back to space. So that's a cooling effect that leads to lower climate sensitivity. So that's the reason why we think this observed SST pattern leads to lower climate sensitivity. But in the future, as this Eastern Pacific cooling, the model world, it always project El Nino-like more enhanced warming in this region. This west gradient gets flipped sign, then we start to see this low clouds break out and then allowing for more shortwave radiation coming back to surface to warm surface temperature. So that leads to higher climate sensitivity. So to wrap up this pattern effect or climate sensitivity problem, before I was showing you this discrepancy between observed energy budget and couple model future projections, I show you the discrepancies, and this is essentially due to the differences between observed SST pattern and future projected SST patterns. The implication is that if we trust model future projections, then we should expect this higher climate sensitivity as the model projected. And so far we've tested for asymmetric model physics, asymmetric models. If they gave them, if you give them realistic SST patterns, then all the asymmetric models do a pretty decent job of capturing the model, the observed energy budget, suggesting that model physics are probably overall fine to represent the realistic energy budget. But the question still remains as, what about fully coupled models? If you force a fully coupled models with all the realistic historical aerosol forcing, CO2 forcing, volcanic forcing, could these fully coupled models reproduce these observed SST patterns? That's the question we want to ask. Well, if so, if models can do a pretty decent job reproducing these observations, then probably models are fine, and their future projections are also reliable and informative, then we should prepare towards this kind of a El Nino-like SD pattern and therefore higher climate sensitivity. But if models are wrong, models can't capture this observed pattern, then that's a bigger problem. Then we should worry about it. We should put a question mark on their future projections. We need to understand why that's the case. So let's look at model historical simulations. My collaborators and I have looked at 16 large ensembles in SIMI 5 and SIMI 6. So all these historical simulations over this recent decades to be compared with observations. And we find over nearly 600 ensemble members. None of the ensemble members can actually simulate an SST trend pattern closer to observation. Like overall models produce too much warming in the Eastern Pacific, too much warming in the Southern Ocean. They basically miss the enhanced west-east gradient. They miss the tropics versus Southern Ocean, this meridional gradient. They can't capture this SST pattern and therefore climate sensitivity energy budget from this recent period. There's a huge model biases. Of course, you may wonder, well, observation is only one realization that could be influenced by natural variability. And here I'm just showing you the multi-model, multi-ensemble mean, which essentially shows you the force response. How do we reconcile these two patterns? So we also looked at large ensembles. We're counting for internal variability. For example, here, A to P is essentially 16 models, all of these ensemble members. And I took some index, for example, tropical west-east gradients with one index, and Southern Ocean zonal mean temperature, one index. And for tropical west-east gradients, you see observation, which is the red dots and the black lines. Observations show positive values, which means La Nina-like or enhanced west to east gradients. But nearly all of the ensemble members simulate the opposite, like weakened or like El Nino-like SD pattern. This is for the tropic Pacific. And for Southern Ocean, same. Observations suggest a negative trend, so cooling trend, zonal mean. But large ensembles, except these two models, nearly all of the ensemble members simulate a warming trend over this historical period. So clearly something is going wrong here. Either models don't have large enough natural variability. Their natural variability is not wide enough, or models have some biases in their force response or forcing. So what caused this? So it opens another big question. What caused this observed SST pattern over the recent period? If this SST pattern was largely influenced by just pure natural variability, for example, just some extreme negative phase of a PDO, for example, or IPO, and then models don't capture that simply because models happen to miss that phase, then in that case, we probably could say model simulated a force response and the future climate change might be still reliable. And we should prepare towards this kind of eventual El Nino-like and Southern Ocean warming pattern. And that means we're going to eventually see higher climate sensitivity as model projected, and therefore greater warming in the near future. This is one scenario. But what if this observed SD pattern was actually largely a force response? For example, it could be a force response to a transient force response to CO2 forcing or aerosol forcing or other non-CO2 forcings. And then models don't capture that because models overall systematically share biases in their forcing or force response or their mean state. Well, in that case, then the model future projections might be also problematic. Then we should put a question mark on that, and we should be concerned about the future projections. And we should probably expect this observed SD pattern, if it was forced, then under continued future forcing, then this SST pattern along with lower climate sensitivity might persist longer into the next couple of decades or centuries. In that case, we might prepare for muted warming in the near future. So you can see, understanding this, the policies of the observed SST pattern and why models fail to produce that is an extremely important question, because it matters for how we accurately understand what's going on in the current climate, the current climate dynamics. And it also matters for how we accurately project the future climate change, what kind of a pattern and the climate sensitivity we should expect to see in the future. So that's this whole pattern effect of climate sensitivity literature really motivates me to understand what causes ST pattern. And among many proposed theories, I'm going to focus on the one idea, which is the tropical Pacific ST pattern might be influenced by the Southern Ocean through the remote impact. And for the Southern Ocean cooling, there are also a lot of proposed theories. So I'm going to focus on this Antarctic ice sheet to meltwater impact. I think usually when I talk this work to tropical cloud feedback or tropical Pacific community, I usually spend a lot of time explaining what Antarctic ice sheet meltwater is. But I guess for this community, I probably can quickly skip this part. So here we just consider the freshwater input from Antarctic ice sheet, the ice shelf melting, which has been proposed to be at least one of the candidates to explain the observed Southern Ocean surface cooling trend over recent decades. And here just showing sub-modeling studies from our GIS model. I think this is from Craig Wright with the idealized abrupt fresh forcing input to the GIS model. And with this abrupt freshwater input, you can see the Southern Ocean start to show some cooling anomalies on the surface and warming anomalies at the depth, along with surface freshening response due to this increased ocean stratification. And this is not only seen in GIS model, but also a wide range of models, including CES1, which I'm going to use for further studies. So far for all of these modeling studies, I think they nicely show the Southern Ocean temperature, salinity, and Antarctic sea ice response. Yeah, sea ice response to ice sheet melting. But the question I want to ask is, does meltwater have a remote impact on the tropical Pacific, which we cared about for climate sensitivity and therefore global surface warming rates? That's why I decided to take some meltwater simulation to study this problem, and luckily got a lot of help and support from my colleague Andrew Pauly in the University of Washington and Shaina Sadai here. They both run some simulations with meltwater hosing using CES1 Camp 5. And both are transient simulations over Angel simulation focused on the historical period, recent four decades, and the Shaina simulation focused on the 21st century. Although I think her simulations extended to 2250, 2200, but here I'm going to focus on the 21st century, both with realistic time varying historical and RCP 8.5 radiative forcing. So for historical ensemble, we increased the number of ensemble members after the publication of Andrew Pauly's paper. Now we have 9 ensemble members. Each is branched from slightly different initial conditions, so branch different large ensemble members. And for this set of simulations, we imposed an abrupt and a constant and idealized amount of fresh water, which is 2,000 gigaton per year at the depth, so at the interior freshwater forcing, to mimic that, or as if all the fresh water was from basal melting. And and for this particular set of simulations, we only account for salinity changes, so salinity flux changes without latent heat. And I have to be clear that this amount of fresh water we imposed is actually higher than the best knowledge we have for observational constraints. So based on Craig's earlier paper, this amount of fresh water we use for CES1 for this particular model is actually much higher than observation constraint. And later I'm going to show that the one of the caveat that still for this model we see the response is magnitude of the response is weaker than the observed trends. So this is for the historical ensemble. For the 21st century ensemble on the RCP 8.5, there's only one simulation, but Shaina, I think she imposed a lot more freshwater forcing. It's pretty strong freshwater forcing, estimated by separate offline ice sheet model, similar force by RCP 8.5. So at the end of the 21st century, the total amount of fresh water from liquid and solid is pretty high, definitely higher than the historical period. And because she accounts for both liquid and solid, so essentially this simulation also accounted for latent heat used to melt the solid freshwater or ice discharge. So before I show some remote and global impact, I'm going to first quickly show you some local changes in the Southern Ocean so you can compare with previous like a GISS model simulation and observations to validate the CES1 simulation. So here is just the zonal mean, Southern Ocean zonal mean potential temperature trends in color and salinity trends in contours from our historical ensemble on the top and 21st century simulation on the bottom from control run without meltwater, so just radiative forcing, and with meltwater and the net difference. And you can see both simulations, both sets of simulations, the imposed meltwater can induce anomalous surface cooling trends and subsurface warming along with surface freshening, which are quite consistent with the GISS model and other climate models. And also bring the model closer to the observed trend. So this is observed Southern Ocean potential temperature and salinity trend from EN4 observational dataset. Although here the magnitudes of the cooling and freshening are still weaker than observation, but start to make the model closer to observation by producing this net cooling trend and the surface freshening trend compared to the simulations without meltwater. So this is for the Southern Ocean local response. And now it seems like CES1 is doing reasonable response compared to other models. So we're ready to move to remote and global impacts. So this is the SCD trend patterns I wanted to look at from the simulations. Global SCD trends over historical period, over 21st century from just radiative forcing simulations with meltwater and the difference. And you can see the meltwater induced Southern Ocean cooling is not confined locally. It further propagates to the low latitudes in the subtropics and further make it to the equatorial Pacific, so that our meltwater runs with radiative forcing now can simulate a net cooling trend in the Southeast Pacific and Southeast Pacific sector of the Southern Ocean and also the tropical Eastern Pacific, which makes the simulation looks more like observation. Again, the cooling trends are the simulated historical cooling trends are weaker than observation, but this overall pattern starts to look closer to observed pattern as it featured this enhanced west-east gradient and some Southern Ocean cooling trends compared to the simulations without meltwater. Also in the 21st century, in the future projections, if we continue to account for this future meltwater forcing, then China simulation suggests that 21st century might see this La Nina-like cooling pattern, like recent observed La Nina-like SD pattern persist into the 21st century. So that's a big impact, remote impact on the global SST patterns. Oh yeah, just accounting for meltwater better simulate the observed global SD pattern.
You had a question in the chat.
Okay, I think.
It was answered. It's fine. Thanks.
Okay. Yeah, this was 9, right? So this ensemble mean of 9 ensemble members. And the individual people observed, and the individual models observed at amplitudes. Other, why is the ensemble mean pattern looks pretty? Sorry, I mean, yeah, sorry. No, like either the global patterns or the some like regional index, we found the non-ensemble members can simulate the either cooling trends as strong as observed. And overall, the ensemble mean feature definitely a different pattern, like El Nino-like, and then enhance the Southern Ocean warming. So this overall pretty, I would say, systematic biases across ensemble members in Simmons 5 and Simmons 6 archive. Oh, it's a constant 2,000 gigaton per year, and it's not wrapping up.
So that's constant from 1980.
Yes, it's abrupt for, it's kind of abrupt for time series type of simulations. It's abrupt and then constant sustainability.
Okay, okay, thank you very much.
Yeah, yeah. Yeah, so here I was very excited to see this remote impact on the tropics. And regarding this remote impact or teleconnection, I think here I say teleconnection, I think actually in atmospheric science community, when we say teleconnections. Usually people think of how tropics influence ectropics. For example, how ENSO influence mid-latitudes, weather extremes or precipitation or circulation. But here we're really talking about the other way around, how high latitude, especially the Southern Ocean, influence the low latitude. And at the end of my PhD work, I started to look at the other branch of the teleconnection, and there are quite some work establishing the mechanism for this, the teleconnection. For example, a classic view has been associated with zonal mean heat transport. For example, if you have colder southern hemisphere and warmer northern hemisphere, then you would expect the ITCZ, the tropical rim belt, shift towards warmer hemisphere as required by large scale heat transport. And this will be associated. This will cause changes in cross-equatorial surface wind and therefore tropical SST changes, tropical SSTs. So this is more like a classic view how large scale or zonal mean heat interhemispheric temperature gradient might influence the tropical climate, precipitation, tropical SSTs, and circulation. This is one classic view. A more recent to a lot of the papers, a lot of work, including my own work, has been focused on more regional dynamics. For example, we found that if you have a more warming in the southeastern Pacific sector of the Southern Ocean, and this region can be efficiently linked to the tropical Pacific because the climatological mean winds, the southeasterlies near the Andes, can efficiently advect surface temperature anomalies into the tropics. Now, once you have this initial surface temperature anomalies, there are a lot of processes can amplify this cooling response in the low latitudes. And this process include ocean process such as coastal upwelling, so ocean upwelling response, or atmosphere-ocean coupling, such as wind evaporation SST feedback through latent heat, or it's purely just atmospheric feedback, like top atmospheric cloud feedbacks can amplify this cooling. So a lot of a process can, through circulation or energy budget, can further amplify this cooling, essentially establish this large-scale teleconnection from the Southern Ocean to the tropical Pacific. I'm happy to talk more about this dynamical pathways. This is currently the focus of my current work. But for now, I think with this, we're excited to see all this mechanism at work at this meltwater simulations. So with meltwater, we also see this cooling can propagate to the tropical Pacific, setting this large-scale teleconnections. And we cared about this because essentially for the tropical, once you have some changes in global SST patterns, it may change our estimate of climate sensitivity. And indeed, when I performed this energy budget analysis, and we found net radiative feedback, the lambda terms becomes more negative, which gives you lower climate sensitivity. You can see from 3.5 degree to 3.1 degree in historical period. And over the 21st century, we'll also see the same like reduced effective climate sensitivity estimated from this period, solely coming from the change in SST patterns. And this is because the change in SST patterns propagated to the tropics Pacific change the subtropical or tropical cloud feedbacks linked essentially coming from the increased LCC, which is low cloud cover. So as we observed over the historical period, this La Nina-like SST pattern increased low cloud cover in the Eastern Pacific, which enhanced shortwave reflection to the space. So that essentially gives you a very negative or strongly stabilizing feedback in the subtropics. So this is quite, I think, quite interesting piece of the results in our simulations. We found adding meltwater into the Southern Ocean not only changed Southern Ocean locally. Of course, here we didn't examine Antarctic sea ice or too much emphasis on the Southern Ocean locally, but we found that it can actually drive a pretty remote impact on subtropical cloud feedback and therefore global climate sensitivity. Should I pause here? I just realized a lot of questions in the chat. Should I pause here and answer some questions?
Yeah, it looks like they were
just most of the
partially
comments
answered.
were.
But there's a question about why.
Oh, thanks, Gavin. I think you, yeah. Simple goal, yeah. Cooling just increase. Yeah, mostly because putting fresh water into the Southern Ocean increase ocean stratification, therefore reduce this upward heat transport from the relatively warmer subsurface to the relatively colder surface. So you prevent this upward heat transport, therefore results in more surface cooling at the surface, more surface cooling surface, and more warming at depth. Yeah, so in the last piece, so now we see the fresh water from the Southern Ocean can have a remote impact into the tropics and therefore change global acidity patterns and climate sensitivity. And also here I'm just plotting the global mean transient warming rate from our two sets of simulations, but also in Shanna's paper or in Andrew Pollin's original papers, they both document how adding meltwater can reduce global warming on transient timescales. So the last question we want to ask is that we see in mostly, well, almost in all of the models, adding meltwater can reduce some regional cooling and therefore globally this reduced warming. But then we want to ask, why does meltwater can reduce global warming? Through the from this energy budget perspective, is through ocean or through this atmosphere or top atmosphere radiation changes? So let's come back to this simple schematic atmosphere ocean simple box. So I explained before, like on a transient time scales, we have radiative forcing, CO2, aerosol, others can change the global mean surface temperature. We see this delta T. But this delta T essentially on transient time scales essentially governed by two terms. One is the amount of heat lost or emitted at the top of the atmosphere. So it's governed by radiative damping at the top of the atmosphere. And this is governed by radiative feedback, like cloud feedbacks or water vapor feedbacks. So this is through atmospheric process. But at the same time, it's also determined by how much heat is taken up by the deep ocean. So the ocean heat uptake, how efficient ocean heat uptake is. Both terms can contribute to or can control how much warming we're going to see in response to forcing. And so far, I've showed you radiative feedbacks. As feedbacks become more negative, more stabilizing, meaning that we have more efficient radiative damping at the top of the atmosphere. And this is due to the acidity pattern effect, because this La Nina-like tropical acidity pattern enhance the strength of low cloud cover, therefore reflects more solar radiation. So this for this part, the upward heat loss, radiative damping. But at the same time, we find ocean heat uptake efficiency also becomes stronger, meaning that more efficient ocean heat uptake. We calculate this parameter, we found stronger, and this qualitatively is because as Gavin explained earlier, because fresh water increase ocean stratification, therefore make ocean more stratified, more heat is being stored in the deep ocean, while keep the surface cool. So it's a pretty efficient ocean heat uptake of process that can reduce conserve temperature. So at this point, we find meltwater overall can reduce global warming rate, but we find it's corresponding to both a stronger feedback and more efficient radiative damping at the top of the atmosphere and more efficient ocean heat uptake. Both terms, both angles can reduce global warming rate. So the last question we want to ask is, which term plays a bigger role? Which term contributes more? What are the relative roles of the changes in feedback versus change in ocean heat uptake? So we performed this energy budget analysis and simply just calculated this contribution to warming, and I find over historical period, it's half and a half. Half of the reduced warming is coming from stronger feedback, and the rest of the half is coming from stronger ocean heat uptake. But for future ensemble in Shannon simulation, probably because stronger cooling in the tropical Eastern Pacific, so stronger feedbacks, so essentially we found over half, like 2/3 of the total change of global warming is coming from this strengthened cloud feedback, while only small, like 1/3 of the total amount of global warming, global relative cooling is coming from ocean heat uptake changes. So we think this is another interesting result we learned from this set of simulations, because so far when we talk about meltwater, especially for ice sheet community or ocean community, we tend to think of how meltwater change ocean stratification, ocean heat uptake, therefore change global warming rates. But here we find because of the atmospheric remote impact onto the tropics, this meltwater actually can have change global warming rate also through feedback changes, through tropical cloud feedback changes. And these feedback changes contribute as substantially or sometimes can be even stronger than ocean heat uptake efficiency changes in reducing the global warming rate. Yeah, so this is I found this result quite fascinating, that we imposed fresh water. We didn't change any radiative force in just water mass balance or salinity anomalies in the Southern Ocean, but end up seeing this stronger change in the subtropical cloud feedback changes. Yeah, so let me, I think, so quickly summarize the results I showed so far. So I started with this climate sensitivity estimate and showed you some interesting discrepancies between historical observed estimate and model future projections. And I argue that this discrepancy, the black line, the blue model projections, are simply coming from the differences in the SST patterns between observation and model projections. So if we trust the model's long-term projections, then we should expect a higher climate sensitivity in the future corresponding to this enhanced warming in the Eastern Pacific. But the question is, models seems like overall have trouble reproducing this observed SST pattern. Of course, here I'm just showing you the ensemble mean, but even looking at individual ensemble members accounting for natural variability, we still find the models have trouble to reproduce this observed cooling trends in the Southern Ocean and in the tropical Pacific. So I thought that this may suggest that these two regions are connected through some remote impact from high latitude. And luckily we found that in these meltwater simulations, we do see both historical period and 21st century, this meltwater can have remote impact, changing the global impact, changing the global SST patterns, and therefore climate sensitivity. So at the end, I don't know if I still have time, what time we should finish. It's quite the end of time.
We can go a little longer. Okay.
I just have one final slide where I sort of summarize some thoughts, open questions, and implications I thought this work can bring to a different community. For example, because I don't consider myself as a polar expert. My past work has been mostly focused on the tropical Pacific and the cloud feedback, but I find this ice sheet meltwater simulations and these results are very interesting in the sense that it probably suggests to, for example, I thought it might be of interest to polar climate community is that the high latitude forcing can actually have a pretty strong remote impact onto the low latitudes or tropical and a global climate. And this could be through changing the global ST patterns, because recent advances in our climate sensitivity studies have shown that ST patterns are indeed crucial for setting the pace of global warming and climate sensitivity. And for climate sensitivity or cloud feedback community, so far a lot of recent interest and attention has been focused on this tropical Pacific, and a lot of this are centered around how we better understand and model observation discrepancies in tropical cloud feedback, tropical SST patterns, and this meltwater simulations to this community is also interesting in the sense that it suggests model biases, like the lack of meltwater in polar regions actually can contribute to this model biases or model observation discrepancies in the tropical Pacific. So another angle adding to the tropical Pacific community. And also accounting for the meltwater in models, like Shannon's simulation suggests, it may change the projected near future of 21st century SST pattern and therefore climate sensitivity estimate in the coming decades and centuries. And for the large scale climate dynamics community here, because I showed the very interesting teleconnection from the Southern Ocean to the tropics, and I said earlier, most of the teleconnection studies in the dynamics community has been focused on how Rossby waves or asymmetric bridge linking ENSO region tropical Pacific to mid-latitude weather, circulation, precipitation. So we really need more investigation, understanding of how different asymmetric oceanic pathways linking this two-way interaction between the tropics and ectropics. And finally, for sea level rise, climate impact community, I know, for example, Shanna has done a lot of work looking at sea level rise and the various climate impact. I just find like this simulations linking meltwater to climate sensitivity and energy budgets can suggest or provide a very interesting angle which is the strong coupling between various climate change signals. For example, here initially we impose meltwater simply motivated by this biases in water mass balance in the Southern Ocean or around Antarctica, but ends up because, well, this fresh water ends up driving tropical cloud changes, which change the global energy budgets. So this coupling between the dynamic coupling or energetic coupling between various climate change signals across time scales, across spatial scales, it's the most fascinating thing to me to learn about the global climate dynamics, the coupled climate system. Yeah, so there are just some thoughts and potential link to some open questions and implications, and I hope can be of interest to many different communities. Yeah, I think this is my last slide, and I'm happy to take any questions. I think there's a question in the chat.
Thanks very much.
Should we go from the top to the questions?
I think there's a question from Jeff on the
Great range and impact of fixed holes in different climate models. The difference is due to the base stratification of the model. That's the impact is not a guaranteed result. Yeah, I agree. I think this, so far we've been focusing on CES1, and the result could be very model dependent. Like with for example, even with the same amount of fresh water, how Southern Ocean responds, how tropics respond to Southern Ocean cooling, and how tropical cloud feedbacks respond to tropical cooling. All of this process can be model dependent. For example, we find this reduced climate sensitivity in CES1 indeed both quantitatively and qualitatively might be model dependent, this result, which means it would be a very interesting question to explore this model spread. For example, I would imagine this whole process, as I said, tropical local, Southern Ocean local response, teleconnection, and tropical clouds, all of this process could contribute to the total intermodal spread. And to me, the question is like, which part is mostly, as Jeff said, is mostly due to Southern Ocean mean state biases, or due to this large scale circulation pathways intermodal spread, or due to tropical cloud feedbacks? I think that's actually a pretty interesting question to further explore.
And there was a question from Gavin
what are the biases for the stratification expected to enhance or dampen the response to fresh water? Bias in CF1 for the stratification, you mean like a mean state stratification biases, or response to fresh water?
Yeah, mean state. I mean, is it overly stratified or is it under stratified?
Yeah, that's a good question. I think CES1 remains. I think it's less. Maybe Shanna can correct me if you looked into this question. I think based on Andrew Pollan's historical simulation compared to other models, CES1 remains as one of the models who is less sensitive to freshwater forcing. So like this model needs a lot of fresh water to really change stratification, and therefore give you this Southern Ocean surface temperature anomalies. So I think this remains that's a less stratified class of models. I think it's different to GFDL models. For example, I remember in GFDL models, you have stronger natural variability and less mean state biases. But if you put fresh water, I think in their simulations, we end up seeing less tropical SDU response and Southern Ocean SDU response to meltwater forcing.
Thanks.
Do we have any other questions? We're at 12 o'clock, so.
Yeah, sorry for the delay at the beginning.
Yes, Jeff, another question.
Hi, yeah, can you hear me?
Yeah.
So there's been some papers by Shona McKay who showed that it depends on whether the fresh water comes from icebergs or subglacial melt. And so you get different results, but if you're putting the water in at the surface rather than in at 700-meter depth, say, then you're getting you're putting all the fresh water at the surface, and you expect more of a surface response. There's surely some deep circulation response, like the barotropic stream functions, that might also make a difference.
Yeah, actually, for Andrew Paulin's simulation, he has two sets of simulations. The one we used is had the freshwater at depth, so interior freshwater. But he also had a set of simulations where he only imposed freshwater at surface to account for surface melting. We do see different results, so suggesting that although in his paper he's documenting which depth he imposed freshwater doesn't really change southern Antarctic CS response, but we end up seeing pretty different response in the remote impact in the tropical Pacific, suggesting that's where the maybe ocean circulation or the teleconnections pathways may be sensitive to where the forcing is imposed or where the forcing is from, at the surface or at depth.
Oh, incidentally, there's another project, I don't know if you've heard of it, called SOFIA, which is trying to intercompare models with different, with realistic hosing.
Yeah, I've heard, I'm not involved in the project, but I've heard this project from many other colleagues. I'm very excited about this project and looking forward to learning more about this intermodal spread or this kind of a result tested in many other models to see how robust or how the result, for example, we found from CES1 posing other models, or how other models simulates regional, local versus global impacts. I'm very looking forward to learning more about that project.
I think Gavin was asking what the paper that Jeff was referring to. About the, I think about the icebergs versus basal melt. That was a question.
These were papers in 2018 from Shona McKay in working in New Zealand. But yeah, I mean, there have been papers since then looking at the UK models and hosing at different mechanisms, and they've shown that if you hose at depth and have a low resolution model, you can produce the same effect as surface hosing in a high resolution model. So there is a different effect due to resolution, and that's due to the semi-resolved eddies.
As in the higher resolution models, is that higher vertical resolution as well? So presumably less numerical diffusion in the vertical?
Yes. So spatial resolution, of course, and vertical resolution is important. So due to the causing vertical mixing, as you say.
Yeah, I mean, this raises a very interesting question, because if all of the mixing things are in some sense poorly modeled in standard CMIP type runs, then whether they have the appropriate response to a certain degree of freshwater is basically going to be random compared to the real world, right? you know,
Yeah,
there are so many degrees of freedom here, you know, the depth, the whether it goes in as ice or as water, the spatial distribution, you know, I mean, you know, if you wanted to do it like super realistically, you know, you'd have it track the actual basal flow patterns, right? And so you wouldn't put it in everywhere in Antarctica. But then, you know, you'd have to be, you know, there's so many variables, right? So within a GCM, especially within a couple GCM, you know, there's no way that you can both test all of the variations in where climatological meltwater goes, and then all the variations in where this anomalous freshwater goes. Right. I mean, where does the climatological freshwater go in the CSM one? Are you doing exactly the same as that, or are you doing something different?
Yeah,
yeah, go ahead, Shannon, if you want.
I was just writing out a comment in the chat to respond to this, but the meltwater distribution in the U-chair simulation, the freshwater forcing is spatially and temporally variable around the margin of the ice sheet, and that's based off of where the melt was predicted in the ice sheet model that was generating the meltwater quantities. So I was interpolating from the ice sheet model around the coast. So it's spatially varying in that sense. It's not input at depth, which of course does make a difference, though Andrew Pauling's work, which was used for the historical meltwater simulations in this particular study, did test the difference between inputting the meltwater at surface or at depth, and found that there was minimal responses within CESM to the basal forcing versus the surface level forcing. So in mine, it's input at the surface level, spatially and temporally varying based on an ice sheet prediction. And in the newer work that I have, that I never published, even though I did it years ago, but which we are about to publish, the ice sheet model and the climate model are two-way interactive every single year with spatially and temporally varying meltwater.
Right. Okay. No, I mean that's I think we're trying to find a way to have the zeroth order impact without everybody having to have a perfectly coupled ice sheet climate model. Because as we are pretty much, I think, all aware, that is much harder than it's than it needs to be.
Very hard and very expensive.
Yes. So like finding ways that are effective shortcuts, I think is going to be super useful. But you're only putting it in, I mean, you're not assuming any transport by icebergs to deposit water away from the coast.
There's not an iceberg model that's interactive.
Oh, no.
That's
a different question, right? But if you take the climatological deposition of freshwater from the continent, right? That ends up being spread over a wider area than just the grid box right at the coast, right? I mean, like your grid boxes are still inside the ice shelves, as I think, right?
The grid boxes, so the location for the grid boxes is chosen based off of the first coastal cell in CESM to where the ice sheet is in CESM. So like the coast within the ice sheet model and within the CESM ocean mask are different locations, so it's interpolated between. Right.
But in the real world, you know, the ice doesn't melt instantly, and and it travels out, and you end up with a lot of direct freshwater input into the northern reaches of the Weddell Sea and the Bellingshausen Sea, right?
Yep. Yeah. Just trying to do the best we can.
No, I don't know. I mean, there's so many degrees of freedom here, right? So anything that we decide is, in some sense, a little ad hoc and arbitrary, and then you're wondering, you're second guessing yourself even after you spent all this time doing this, whether that was the right choice or not. And we're having this same, debate, and and you know, and then you come to write it up, and it's like, well, how do we explain exactly why we did what we did? And it's all a little like, I mean, not hokey, but arbitrary in some sense, and you keep wondering whether, oh well, maybe you should do something a little bit more realistic, if that would make a difference. And if people keep doing experiments where they say, oh, this tiny little thing makes a huge difference, then that's very disheartening in some sense.
But we have done experiments whereby we've just put meltwater in the Amazon Sea, and it gets mixed pretty well over 20 years.
Yes.
So it looks exactly the same as if you were putting it evenly around Antarctica.
Yeah, but if we look at the sea ice trend over the last 10 years, right, I don't think we're going to be happy if it's okay over a 20-year period to do whatever you want to do, because if something is more sensitive on a shorter time scale, then, you know, we'd want to be thinking that might be important for explaining some of these, like, you know, kind of biennial changes. Like, you know, things are changing so quickly there. It's you know, if things had kept on going slightly anomalously, kind of post 2014, you know, I'd be a lot happier about this as a mechanism. But then, like, everything has flipped, and that is very disconcerting. And I mean, Yui, do you have any? I mean, is there anything that comes out of this that provides any insight into the sudden switch in the sea ice trends?
The sea ice trend. Yeah, I think Andrew Paulin's paper mostly looking at sea ice trend. Yeah, I don't remember much. Like, I didn't really look into sea ice here. But I think, well, for 21st century, actually, this is a recent result from Shannon's simulation. We'll compare with this constant freshwater versus her recent coupling. So she couples global warming with ice sheets melting, and we found in both cases sea ice expands a lot, and then this increased or this reduced this sea ice positive feedbacks. So this also contribute a lot to the onset of or the beginning of the negative feedbacks over the 21st century. Did I answer your question? I think I don't remember much of the sea ice extent over the historical period in Andrew Paulin simulations, but I remember in both
yeah,
old and recent 21st century. Yeah.
Yeah, I've really got to go, but the fact is that when you get the surface cooling, you get an increase in the sea ice, and so if you reduce the surface cooling, perhaps there has been an expansion of land ice, and the net flux into the Amazon Sea has gone down, then maybe the sea ice goes away. I mean, I don't know. We've been looking at it, and we don't have anything. We don't have anything solid. But I have to rush. But this was a great talk. Thank you very much, and let's keep this conversation going. I think there's a lot of interesting stuff to be done here.
Yep. Thanks, Kevin.
Okay, well, I guess we can wrap up there. Anything else? So thanks again, Yue.
Yeah, thanks for inviting me. I actually, yeah, I really I was really excited about this opportunity to learn more about ice sheet melting from this community.
Yeah, I think we had good discussion.
Yeah, feel free to let me know if any of you have any questions or comments on how we can use this simulation to further study other climate change signals. So my email is here. Thanks.
Thank you.